Nowadays, robots are everywhere. Their importance is growing in science, society and industry. They appear in fields, factories, space, sea depths, gardens and in living rooms. Some people think that in the 21st century, they'll be a bit like the 20th century car. Robots haven't just entered industry, they are taking part in our culture's transformation, and sometimes they even take part in how we understand ourselves, humans, in a new way. So, what's a robot? First of all, a robot is a physical machine, provided with a number of engines to produce actions, to produce movements. It also has detectors, or sensors as we call them, that enable it to perceive things in its environment. For example, a camera to see images, micros to detect sounds, force sensors to sense when it touches an obstacle, or when it is bumped into, for example. Infrared sensors to detect things that humans can't see, but animals can. The most important in the definition of a robot is that information is gathered with the environment sensors. It is used to decide which movements will be produced by the robot. So there is a permanent interaction between perception and action. That's what defines robots, as opposed to automatons. For example, Jacques Draws or Vaucanson's automatons in the 18th century, which were amazing machines. Nevertheless, action didn't depend on what was going on around them. They always did the same thing, regardless of what was happening around them. A robot doesn't operate like that. It reacts differently according to what is happening. So in practice, this definition of robots covers a wide range of forms of robots. It can be imaginary robots, humanoid or animaloid robots. But in the end, today, they can only be seen in science labs. This also concerns a lot of robots we live with. Nowadays, planes are widely automated, cars have driver assistance system modes. There are robot vacuum cleaners, for example, or machines that will mow the lawn autonomously. Some toys too. Some fun robots in toy shops, some of which are provided with very advanced technologies. And this diversity of forms covers a rather wide variety of content, operation and mechanism too. So we can talk about a few great dimensions that enable to differentiate mechanisms. A first dimension is the autonomy. Some robots which behavior is autonomous, because actions are done while it is perceiving its environment, without permanent instructions or sometimes just partial instructions given from humans. For example, robots in an automobile factory, which assemble vehicles, sometimes with other robots. Well, if humans don't interfere in the assembling, and robots do it alone, they will be called autonomous robots. However, robots in nuclear plants, which are operated by operators, to go in radioactive confinement rooms, where the operator has a remote control that allows him to define which actions they have to do at each moment, those robots aren't autonomous. Another dimension that differentiates several families of robots is adaptation and learning. Some robots' performance is completely frozen beforehand by a program, and whatever the robot will experience in its environment, it will always behave the same way. On the other hand, there are other robots equipped with other family mechanisms called learning algorithms that enables them to update their action modes and strategy actions according to the events they sense in the environment, according to tests and mistakes they will do. So, for example, there are robots that can explore an environment and gradually build up a map of this environment that will enable them to navigate in it in a rather efficient way, although at first they couldn't. Some mechanisms will allow them to learn to recognize new objects a human will name, To learn to recognize humans' actions, for example, or learn how to move their legs, learn locomotion, for example. These mechanisms are called learning algorithms. They enable machines to detect regularities in what they experience. An experience is made when testing an action and observing the result. It can be repeated a certain number of times. When detecting regularities, they can understand how to predict the result of their action, for example. Concerning how to find a solution, a behavioral strategy, for example to learn how to walk, there are test mistake strategies, for example, where algorithms called optimization algorithms will enable them to gradually refine the settings of these strategies to progressively improve the solution's efficiency. In a number of cases, the solutions found by these machines are quite surprising, or weren't predicted well by the engineer who designed the robot or the learning algorithm. This doesn't mean these robots will invent completely unthinkable things, but for example, it can be a locomotion strategy, a way of using one's body to move which can seem a little absurd for a human. But observe carefully, it is a very efficient strategy, and by using test mistakes, it's the robot which found it. There can also be learning algorithms, a little more sophisticated, that encourage machines to explore an environment and to search for novelty or information to enrich their knowledge. This will allow a machine to develop its know-how list, which wasn't completely programmed beforehand. Nevertheless, we must be careful when saying this, because we could get the impression that the machines are going to be quite intelligent and creative, but in fact, they are still extremely far from adaptation capacities of humans, of animals even, and of more simple mammals. There's still a great amount of work to do before being able to design machines which have the adaptation capacities of a 3 or 4 month old child.